Hello and welcome back. In the past few lectures, we have been discussing generating functions. And in the last lecture, we discussed the exponential generating function and looked at the product of generating functions which are exponential. Now, we also looked at what is the combinatorial interpretation of this product. Now, similar to what we did for the ordinary generating function, we can also talk about the composition of exponential generating functions. So for this, let us start by assuming there are two generating functions, EGFs, where an counts the number of ways of making, let's say, type A structures on an element set. Okay. Where we assume A0 to be 0, just like we did in the previous case. And let us also assume that Bn is the number of ways to put B-type structures on an element set. Now, once we have these two, so we have A of x and B of x with corresponding to the generating functions, exponential generating functions. So we now let another sequence Cn count the number of ways to first partition the set n, right, 1 to n, to non-empty blocks, and then build A-type structures on each block. And then considering these structures as elements, build B-type structures on the set of these blocks. Okay. Then the claim is that C of x is equal to B of A of x. That is the exponential generating function which counts the sequence Cn is the generating function of B substituted with A of x for x. Okay. So this is our theorem. So how we want to prove this theorem? But to make things a little more intuitive, let us see what we are actually doing with the structures when we make the C-type structures. Okay, so here is some nice pictorial representation of what is actually happening. Right. So in this box we have this set 1, 2, 3, etc. Right, 1 to n. Let's say for n is equal to 11 or something. Then what we can say is that we have partitioned the set into different blocks like this, right? So we have this one part is like just including 1 and 2. Then you have a part with 3, 6, and 10. Another part with let's say 3, 4, 7. Then 8 is by itself a part, and then 12, 9, and 11. Yeah, so up to 11, 12 is another part. So we have this. Partition, right? So, and each part is non-empty. Then what we do, we put type A structures on each of these sets. So I can make a type A structure on the 2-element set. Similarly, on this 3-element set, I put an A-type structure. Okay. So there could be several ways of doing this, right? There is precisely A3 ways, right? Small A3 ways of making A-type structures on this 3-element set. Right, that is the definition of the sequence A. Right. Similarly, we have A1 ways of doing this, A2 ways of doing on this set, etc. Right. Now, once we make these structures, right, so we have the A structures on each of these blocks now. Right. Now, consider these as elements and then type a and make a B-type structure on the on this set of A structures. Okay. So then what we get is a C-type structure. Another way to represent this is in the second figure, right, where this figure where we have we have the set. In this case, we have not given any names or anything, but just to we have the set, and then we could of course name them if you want, right? You can make it as 1, 3, 7, 8, 2, 4, 5, right? Something like that. Now, I think I missed one thing. Maybe it's 6. So now what we do, we partition it into blocks. Like, so we have 1, 7, 6 is a block. 3 is a block by itself, 2 and 4 is another block, and 5 is a block, right? Now on each of this block, I put an A-type structure, right? So this represents that I'm making an A-type structure using all these elements. So that is the meaning of this representation, right? And then once we have this, take each of these A structures and then considering them as elements, I make a B-type structure on the set of all A structures that we have, right? So this is what we mean by the composition, right, in the exponential generative function. So now one can ask. What is the proof that C of x precisely counts the B of A of x precisely counts the number of C-type structures, right? So this is something that we want to do. Okay. So I will give you a sketch of the proof. So like in the previous case. So what is the idea here? So we know that we start with set 1 to n, and then we split it into different blocks. Now let us start with the assumption that, when I split into different blocks, it must be, some number. So let us say that there is exactly k blocks, right? So it could be, k could range, of course, from 1 to, 1 to n itself. So therefore, we will fix k for some value, right? And then assume that we have now split into exactly k blocks, and then see what happens. Now, if I do it into exactly k blocks, right, there could be several ways of doing that itself. And then, let us say ck of x is the generating function, right? No, we are not looking at c of x, but ck of x is the generating function for counting the composition in this particular case when I split it into exactly k blocks. I don't look at other values of k, only for this particular value, right? And then I say that, okay, now if I do this, right, I take the set n, 1 to n, and then partition into exactly k parts, then put A structures on each part, and then put B structure on the A structures, right? So if I do that, let us see what happens. Now we know that there is exactly k blocks, right? So each block is basically a subset, right? So take this set, right, on this block, then we put an A-type structure. Now, we are doing this for each of the k blocks. So if you want to talk about the generative function of making A-type structures on each of the blocks independently, then we know that we can obtain this by taking the product of the generative functions, right? So if, for example, we said that if I want to make like a partition into 2 parts, then put A structure on the first type and then B structure on the second type. Then we said that A of x into B of x will give the generative function for doing this. So now we are partitioning into k parts, right? And then putting A structure on each of the parts. So therefore, A of x into A of x into A of x k times will give the generative function for doing this. But there is only a small catch, right? So the catch is that, see, when we were doing the different type of objects, A type, B type, C type, etc., right? So when I take, when I partition, right, and then I put an A structure on the first, B structure on the second, and then C structure on the third, the ordering of these parts actually matters, right? So if I have K parts, the ordering of the parts will matter, because on the first part I am going to put A structure, second part I am going to put B structure, and the third part I am going to put C structure. But since I am going to put A structure on each of these parts, right? At the first block I am putting A structure, second block I am putting A structure, third block also I am putting A structure. So therefore, it doesn't matter which order I have these blocks, right? What only matters is that how many blocks are there, right? So therefore, when I look at A of x whole raised to k, we are basically counting, right? Considering all the possible permutations of the blocks also. So there is exactly k factorial permutations, and each of them will give the same object, because we are putting A structures on them. So therefore, we have to divide by k factorial to make sure that we don't overcome. So this gives the idea that A of x whole raised to k by k factorial is the generating function for ck of x, right? So ck of x, and whatever is the number that we started with, right, n elements, you look at the coefficient of x raised to n in that will give you precisely the number of ways of obtaining C-type structures on n elements by doing this. So what we have shown is that ck of x is equal to but there is another thing, that once you make this, we have to put B-type structures, right? So it's not ck of x. It is just to do the A-type structures on these blocks. Now, then we have to make B structures on the K A structures that we have obtained, right? So that we can do in precisely BK ways. So therefore, ck of x is now BK into AX whole raised to K by K factorial, because Ax whole raised to K by K factorial is the number of ways we can put A structures on the K blocks. And BK is the number of ways to make B structures from the K distinct objects that we have obtained, right? So therefore, it is BK into AX raised to K by K factorial. Now, so if you know for each K, right, what is ck of x, then I can get C of x easily, right? C of x, the generative function for C is basically the sum of all this, because, like when we count it by, separated by the cardinality, right, like of the set in which we are building, our formula itself is the summation over all values of it, right? So summation k equal to 0 to infinity ck of x will give the generative function c of x, which is what we do here. Summation k equal to 0 to infinity bk into a of x whole raised to k by k factorial. But what is this? This is precisely the so if you take b of x, right, b of x is precisely summation bk into x raised to k by k factorial. If I replace x with a of x, I will get precisely summation bk ax raised to k by k factorial. So therefore, it is the substitution of a of x into b, right, b of a of x. So this is the idea of the proof, right? So we have shown that if I take a set, partition into non-empty blocks, put type A structures on the set, then put type B structures on this, on the set of A-type structures, what we get if it is counted by the sequence Cn, then C of x, the generative function for Cn, is the composition of A of x into B, substitution of A of x into B. Okay, so we basically substitute A of x into B. Okay, so that is the composition of generating functions. Now let us see some application for this. Our first example is the following, that we have a number of ways, let's say, to partition a set of n people, right? And we want to count the number of ways to partition a set of n people, and then once you partition, we want to put each block of people and ask them to sit around in circles. Okay, and the claim is that this is precisely n factorial, right? So we are basically partitioning people, n people, n persons into blocks, and then ask each person to not each person, each block of people to sit around in circular tables. So you have like circular tables with chairs on around it, and we will ask these people to sit around let's say these tables. Now, how many ways one can do this? So the claim is that this total number is n factorial. Right? So let us prove this using the composition of generative functions. So let us denote by ak, right, as the number of ways the people can sit around in circles, right? So basically, what we were doing in the exponential generative function was that you split into k blocks, right, and then you put type A structures on each of the blocks, right? So here we are asking the people to sit around in circles, right? Each block people to sit around in circles. Now, if there are k people in a block, right, then there is k minus 1 factorial ways to put them in circular way, right? So circular permutation, that is precisely k minus 1 factorial. So therefore, we know that the generative function for this, right, for people to sit around in circles is summation n minus 1 factorial into x raised to n by n factorial, which is the exponential generative function. And what is that? This is summation x raised to n by n, right? Because n minus 1 factorial and n factorial cancels out, you get n, and which is log of 1 by 1 minus x. Right? This is something we already have seen. So the generative function for making the type A structure, which is a of x, is log of 1 by 1 minus x. Now, what else we do? So we partition, and then we are just asking them to sit around, but then we are not doing anything, right? We are not making B type structures. So if we are making B type structures, then we could use the substitution. But if we are not doing the B type structures, what exactly can we do? So if you think about it, like when we do nothing, that there is precisely one way to do it, right? Do nothing, right? So we partition, right? Make these hash structures and then do nothing, right? Which means that we are doing precisely one way, right? So the coefficient of bk or bn for any n is precisely 1, because no matter how many blocks are there, we have exactly one way of doing nothing. So b of x is now summation 1 by n factorial x raised to n, because we are looking at the exponential generative function. What is that? This is e raised to x. We already saw this several times. So therefore, b of x is e raised to x. So now the composition b of a of x is x is substituted by a of x in e raised to x. So e raised to log of 1 by 1 minus x, which is 1 by 1 minus x, right? Which is the generative function for c of x. Now, what is the coefficient of x raised to n by n factorial in the series expansion of 1 by 1 minus x? So 1 by 1 minus x is summation x raised to n, but then we want to look at the coefficient of x raised to n by n factorial in this, which is precisely n factorial, because we want to multiply and divide by n factorial to make the coefficient be 1. And that is what we have, right? So n factorial is the number of ways of making the C type of C type structures on n element sets, which is basically asking the people to sit around in circles, right? So this is there is n factorial ways of doing this. Okay, now let us look at one more example, which is slightly related. So find the number of ways to separate n people into a number of groups, and then let them sit around again in circles. But then after sitting them on tables, we serve them with either juice or water, right? So this is what we do. Now, how many ways of doing this, right? So how do you count this, right? So we can use the same idea. So we know that a of x is log of 1 by 1 minus x, as we did before, right? Asking people to sit around in circles after partitioning them, right? So a of x is log of 1 by 1 minus x. Now, what is bk, right? If there are k blocks and we are serving either water or juice to the tables, there is precisely 2 raised to k ways of doing this, right? We can decide whether to give water or juice. Therefore, two choices, and we have 2 raised to k possibilities for the k, right? We can do that, and therefore b of x is the generative function for the type B structures on these tables, right? Is the precisely summation 2 raised to k x raised to k by k factorial, which is e raised to 2x. Now, e raised to 2x, we have c of x is e raised to 2, and then x is distributed by log of 1 by 1 minus x, which is 2 log 1 by 1 minus x, which is 1 by 1 minus x whole square. And we know that the series expansion is summation n plus 1 x raised to n. But we want the coefficient of x raised to n by n factorial. So therefore, we multiply and divide by n factorial, I get n plus 1 factorial, right? So there is n plus 1 factorial ways of doing this. And this is kind of surprising because when we, when we do this, 2 raised to k is coming, right? Like when we do this serving of juice or water, that, somehow, like we will feel that like there is the factor of 2 must be coming, but that is, right? Like 2 raised to k must be present somewhere, but that is not the case. So it is nice to see that we get n plus 1 factorial as the number of ways of doing it. So these are two examples of using the composition. I mean, one can have several other examples, but let me now go to some few other things. I am going to give an application into let's say RNA counting RNA sequences, and similarly I want to also look at an application of generative functions at the end to wind up this topic, where we will prove Euler's famous pentagonal number theorem. Okay, so these two are the applications, and with that we will wind up this part. So here is an example with RNA counting. So we want to count the number of RNA chains with some conditions. So what is a K-link RNA chain is basically an ordering of the nucleotides. So what are the nucleotides? One is adenine, then you have guanine, then cytosine, and uracil. Okay, so these are the nucleotides which are present in RNA chains. If you are looking at DNA chain, then you will be replaced by something else. But other things are there. But then there is some differences. So what we are going to do here is to count the K-link RNA chains. Okay, so where I want to specifically count the 2-link and 3-link chains. And so basically a chain is an ordering of the letters A, G, C, or U, where A, G, C, U represent the nucleotide, which are the molecules. Now, how do we do this, right? So we have the condition that we are allowed to use at most 3 adenine or 3 guanines, 2 cytosines, and 1 uracil. These are the only things available, out of which we want to make 2-link or 3-link RNA chain. So how do you do that? So here is a solution. So we are going to prove a little more general question first, and then as a special case, we will solve the RNA coding. So suppose we have p types of objects. Okay, so p different types of objects where for each I, the type I object, there is the ni of them available, right? So in this case, we had type A objects, there were 3 of them. Type G object, there were 3 of them. Type C object, there were 2 of them. And type U object, there was 1, right? So similarly, type I object, there is ni of them available. Then the number of distinguishable permutations of length k with at most ni objects of type I, right? To draw from is the coefficient of x raised to k in the following generating function. So can you guess what is the generating function for this? Okay, so think about this for some time before proceeding further. Okay, so it should be clear if you have understood how the generative functions work, that I can take the product of 1 plus x square by 2 factorial plus etc. x raised to ni by ni factorial to represent, so this summation of 1 plus x etc. x raised to ni by ni factorial represents the choice of either 1, 0, 1, 2 or up to ni of the type, let's say, I object, right? So then I take the product, I ranging from 1 to p. This will tell you that if I'm looking at most, let's say, n objects, that I'm drawing exactly n objects, then the coefficient of x raised to n in this product will tell that, okay, from the the first factor, which is 1 plus x etc. x raised to n1 by n1 factorial, which term I have chosen, that will tell you how many copies of the type 1 object I have chosen, right? So if I take x square by 2 factorial, that will tell me that I am choosing 2 copies of the type 1 object. So similarly for each type I, and therefore that is the generative function, right? And so the generative function for the RNA chains is basically, you substitute for each of the type I objects with the corresponding numbers. So 1 plus x square by 2 factorial plus x cube by 3 factorial for the type A and type G objects, right? Because both of them have 3 of them. And therefore it is square of this polynomial. Then we have 1 plus x square by 2 factorial for the type C object. And for the type 1 object, there is only 1 available. So either 1 or 0 I can choose, 1 plus x. And hence, you take the product of these polynomials, you get a polynomial and look at the coefficient of x square by 2 factorial. And one can verify that it is actually 15 in this case. And if you look at the coefficient of x cube by 3 factorial, you can verify that it is actually 53. And that is precisely the way to count this. And one can generalize it to other examples very easily.